Equation 1, epsilon equals phi, times the square root of the quantity, pi plus e. On the surface, this seemingly innocuous equation appears to be a simple combination of mathematical constants. However, upon closer inspection, it reveals itself to be a profound expression that may hold the key to understanding the fundamental nature of reality. The golden ratio, pi, and Euler's number are three of the most enigmatic constants in mathematics. Each has been extensively studied and applied across various disciplines, yielding insights into geometry, algebra, and calculus. The introduction of these constants in a single equation hints at an attempt to bridge disparate mathematical concepts, potentially uncovering hidden relationships between them. The result, epsilon, is an unknown constant that remains shrouded in mystery. Its calculation involves squaring the root of the sum of pi and e, which, in turn, is multiplied by phi. This operation can be seen as a harmonization process, where disparate elements are brought together to form a unified whole. One possible interpretation is that epsilon represents an underlying structural element governing the behavior of complex systems. The golden ratio, pi, and Euler's number have been linked to various natural phenomena, such as the proportions of biological structures, the geometry of crystals, and the distribution of prime numbers. By combining these constants in a single equation, we may be tapping into a deeper level of organization that permeates the universe. The potential implications of this equation are far-reaching. It could be seen as an attempt to quantify the essence of beauty, harmony, or balance that exists in the natural world. The golden ratio, for instance, has been observed in the arrangement of leaves on stems and the branching patterns of trees, suggesting a universal principle governing growth and form. Furthermore, the presence of Euler's number in this equation adds an element of unpredictability, introducing chaos and randomness into the calculation. This may be seen as a reflection of the inherent uncertainty principle at play in quantum mechanics, where the act of observation itself influences the outcome. The relationship between pi and e is particularly noteworthy. These two constants have been shown to appear in various mathematical formulations, often describing seemingly unrelated phenomena. The connection between pi, a fundamental constant of geometry, and Euler's number, a measure of exponential growth, may hint at a deeper unity underlying different areas of mathematics. In conclusion, equation 1 is more than just a mathematical curiosity, it may be a key to unlocking the secrets of the universe. By exploring the properties and implications of this equation, we can gain insights into the intricate web of relationships that govern our reality. Whether seen as an expression of harmony, balance, or chaos, this equation has the potential to revolutionize our understanding of the natural world and inspire new areas of research in mathematics, physics, and beyond. As we continue to unravel the mysteries hidden within this enigmatic equation, we may find ourselves on the cusp of a profound discovery, one that could fundamentally alter our perception of the universe and our place within it. The pursuit of knowledge is often driven by an insatiable curiosity about the nature of reality, and equation 1 embodies this spirit in its most refined form. Equation 2, delta x equals the quantity 1 minus e to the power of negative t times the sine of pi over 4. At first glance, this seemingly complex equation may appear to be an intricate combination of exponential and trigonometric functions. However, upon closer examination, it reveals itself to be a powerful tool for describing the dynamics of motion in classical mechanics. The equation describes how position, delta x, changes over time t, with two primary components, exponential decay and oscillations. The exponential term, e to the power of negative t, represents a gradual attenuation, or diminution of some quantity, while the sine term, sine of pi over 4, embodies periodic oscillations. The combination of these two terms yields an equation that is both continuous and oscillatory, capturing the essence of real-world motion. In classical mechanics, objects respond to forces by changing their position over time, and equation 2 provides a mathematical framework for modeling this behavior. One possible interpretation is that delta x represents the displacement of an object under the influence of a force. The exponential term could describe the gradual decay or attenuation of the force over time, while the sine term captures the oscillatory nature of the motion. This equation may be applicable to a wide range of physical systems, from the motion of particles on a surface to the vibration of strings. The potential implications of equation 2 are far-reaching. It could be seen as an attempt to describe the fundamental laws governing the behavior of objects in the physical world. The interplay between exponential decay and oscillations may provide insights into the underlying mechanisms driving complex phenomena, such as the motion of celestial bodies or the behavior of subatomic particles. Furthermore, equation 2 has implications for various fields beyond classical mechanics. In signal processing and communication theory, similar equations are used to model and analyze signals that undergo attenuation and filtering. The oscillatory component may be relevant in fields like electrical engineering, where the study of circuits and resonance is crucial. The relationship between time and position is particularly noteworthy. This equation demonstrates how an object's motion can be influenced by a force that decays over time. In classical mechanics, forces are often described as being proportional to acceleration, with the acceleration itself being governed by Newton's second law. Equation 2 may provide an alternative perspective on this relationship, highlighting the interplay between attenuation and oscillations. In conclusion, equation 2 is more than just a mathematical curiosity. It has the potential to revolutionize our understanding of classical mechanics and its applications. By exploring the properties and implications of this equation, we can gain insights into the intricate dance between forces, motion, and time. Whether seen as an expression of decay, oscillation, or resonance, this equation has far-reaching consequences for our understanding of the physical world. As we continue to unravel the mysteries hidden within this enigmatic equation, we may find ourselves on the cusp of a profound discovery, one that could fundamentally alter our perception of the universe and our place within it. The pursuit of knowledge is often driven by an insatiable curiosity about the nature of reality, and equation 2 embodies this spirit in its most refined form. F of x equals x to the power of 1/2 plus x to the power of 1/3 minus x. The first term, x to the power of 1/2, represents a quadratic function that grows at a rate proportional to the square root of x. This term is characterized by its gradual and steady increase in magnitude as x approaches positive infinity. The second term, x to the power of 1/3, corresponds to a cubic function with a slower growth rate compared to the first term. As x increases, this term's contribution becomes less significant due to its smaller exponent. The subtraction of x from the sum of these two terms adds another layer of complexity to the equation. This can be interpreted as a correction, or a balance that adjusts the overall behavior of the function. The presence of this constant term suggests that the function is attempting to maintain some kind of equilibrium between its different components. One striking feature of this equation is its symmetry around the origin, which implies that f of negative x equals negative f of x. This means that if we reflect the graph of the function about the y-axis, the resulting curve would be identical to the original one, but mirrored about the origin. This property makes the equation particularly interesting for applications where symmetry is crucial, such as in physics or engineering. In addition to its symmetry, the equation also exhibits an intriguing connection between its different components. The balance between the two fractional powers and the subtraction of x can be seen as a representation of competing forces or opposing tendencies. For instance, one could interpret the first term as representing a rapid growth or explosion, while the second term represents a more gradual increase or diffusion. The subtraction of x then serves to moderate this growth, ensuring that it does not become too extreme. The graph of this equation would likely display a unique shape, characterized by an initial rapid increase followed by a slower growth and eventually a steady decrease as the constant term takes over. This would result in a curve with multiple inflection points, adding to its visual appeal and complexity. In conclusion, the equation is a rich and multifaceted mathematical expression that embodies several intriguing properties. Its symmetry around the origin, balance between different components, and complex graph make it an excellent subject for further exploration and analysis. As mathematicians and scientists, we can continue to study this equation and uncover its hidden patterns and secrets, ultimately gaining a deeper understanding of the intricate relationships between its various terms. Equation 4. G of y equals y to the power of negative 1/2 plus y to the power of negative 1/3 minus y. This is another intriguing polynomial function with rational exponents. Upon closer examination, we find that this equation exhibits similar properties to equation 3, including symmetry around the origin and a balance between different components. As with equation 3, this equation displays symmetry about the origin. This means that if we replace y with negative y, the resulting expression remains unchanged. This symmetry is a fundamental property of polynomial functions with rational exponents, and has significant implications for their behavior and applications. The equation can be viewed as a balance between three distinct components. The first term, y to the power of negative 1/2, represents a function that shifts drastically as y approaches 0. The second term, y to the power of negative 1/3, is an even slower shifting function that dominates the behavior of the equation for larger values of y. The subtraction of y serves to correct or balance these components, ensuring that the overall function remains bounded and does not diverge. This balance is crucial in understanding the properties of equation 4, as it determines the shape and behavior of the corresponding curve. The symmetry and balance properties of equation 4 suggest a deep connection to algebraic geometry. This equation may be used to describe the properties of curves or surfaces that exhibit similar symmetries and balances. In particular, the equation could be related to elliptic curves, where the symmetry is reminiscent of the elliptic curve's symmetry under the action of a group, and algebraic curves, where the balance between components may be related to the algebraic structure of curves, such as the intersection of two or more algebraic sets. These connections have significant implications for the study of equation 4 and its potential applications in various fields, including computer science, physics, and engineering. The graph of equation 4 would likely display a unique shape, characterized by an initial decrease followed by a slow increase and eventually a steady decrease. The symmetry would result in a curve that is reflective across the y-axis. In conclusion, equation 4 presents a fascinating polynomial function with rational exponents, characterized by symmetry around the origin and a balance between different components. This equation has significant implications for algebraic geometry, potentially describing the properties of curves or surfaces that exhibit similar symmetries and balances.